I'm owner of a small practice, Boeman Design LLC. I'm relatively new to Passive House. I got certified about 4 years ago now, and my prior career was in commercial interiors. So worrying about things like mechanical systems and envelopes is actually pretty new for me, but it's an area of great interest. And to me, this is an opportunity to both share what I do know and educate myself on it a little bit deeper. So Passive House's standard is put out by the Passive House Institute US, and they're one of several Passive House institutes around the world. It originated in Germany as a Passive House Institute. And PHIUS is it's a nonprofit 501c3 organized committed to making high performance passive building the mainstream market standard. So PHIUS trains and certifies professionals. They maintain the PHIUS Plus standard, which is what we're going to be talking about today. They certify and quality assures passive buildings and conducts research into advanced high performance building. And so what is Passive House? So Passive House is used as kind of a term to refer to a couple of things. One is a standard for building energy performance developed by one of the Passive House organization. In this case, we're going to be talking about the Passive Plus standard developed by PHIUS. It also refers to a building that is certified under a Passive House standard. And finally, an approach to the design of high energy performance buildings. So you'll see the phrase Passive House used often interchangeably to refer to any one of those three things. And as a term, Passive House, some people think it should be more properly called passive building because it refers to other than houses. But I actually like the expression Passive House because one of the things it captures is that the house refers not just to residences, but any building where the primary energy use is for maintaining a comfortable space for human beings. So it applies to any building that houses human beings as they live, work, learn, shop, or gather. So it applies to single family homes, multifamily housing projects, commercial buildings, and schools and other institutional buildings. Also, the buildings that aren't primarily about human occupancy might not be good candidate for a Passive House certification. So things like unconditioned warehouses, server farms, automated PV factories, aircraft hangars, parking garages, anything like that that isn't really about human occupancy is not really a candidate for Passive House certification. But there may be exceptions, so if in doubt, run it by PHIUS. Passive in Passive House refers to kind of an approach to energy performance. A passive approach prioritizes the design of the enduring physical components of the building, such as the exterior walls, roofs, windows, and floor on grade. And in some senses, this is kind of a conservation approach. So it's dealing with those kind of things that we're expecting in a building to outlive all of us. And it also, it supports resiliency by minimizing the dependency on active or smart systems. So there are active and smart systems in passive buildings, and they're important. Things like heating systems are always active and smart, but the passive approach tries to avoid depending on them as a basis for their performance. So you'll see that things like automated shading devices, things that move or have a lot of actuators to respond to conditions, are really not in the spirit of Passive House, although they can be used to some extent, and some things are inherently active or smart. And what distinguishes Passive House from other energy standards, kind of the key distinction in my mind is that it's based on a fair share of the CO2 emissions budget that are required in order to avoid global warming by 2 degrees Celsius. And so it's really a per person versus a square foot standard. So you can't really build a Passive House that's extremely huge because inevitably you're going to be using more than the allocation of the CO2 emissions that's really could be properly allocated to each person. So I don't know what the underlying research is that substantiates that, but as you can imagine, most of the energy consumption in this country is well beyond what we would consider the fair share per person. So the passive house standard is designed to kind of get us back in line with what we can expect to consume individually. The PHIUS Plus standard, it's really at the top of the Department of Energy's high performance staircase of standards. So if you look at on the far left on this slide, we have the International Energy Conservation Code of 2009, then the 2012, and you'll see that PHIUS Plus and the PHIUS Plus Source Zero are all the way on the right. They're really the creme de la creme of the performance standards. The difference between the last two columns, the PHIUS Plus and the PHIUS Plus Source Zero, is just whether you actually achieve full net zero versus hitting that per capita benchmark. So in the PHIUS Plus standard, it's based on, certification is based on modeled performance. So the spirit is that you model the building using the WUFI software, and that's a basis of performance with on-site quality assurance and testing and inspection. So those are the two pinnacles, modeling and then on-site quality assurance / testing. And this on-site quality assurance and testing is done during construction. So it's not anything you can do after the building is complete and buttoned up. The passive house project standard is very much something that has to be done during the design and construction of a building. You can't go back and try to get a building certified that's already complete. It's really part of the process. And the quality assurance and testing inspections are based on recognized systems for commissioning buildings from the Department of Energy, EPA, IPA, and ResNet are some of the names. There are always third-party inspection process, so it's an independent contractor does it, multiple site visits, lower door test, ventilation system balancing commission, and insulation inspection. So it's all just to confirm that what's executed is consistent with the model. So the main certification requirements are space conditioning targets, and we'll go through these in detail later, but air tightness, on-site quality assurance and testing that's noted, and net source energy target, and that varies by project. So when you're starting a PHIUS project, you really do it right on the web page. So this on the far right is kind of what the web page looks like, and you go to this what's called the PHIUS Plus criteria calculator, and this is where you give it basic information about your project, and it gives back to you what the criteria that your project will need to meet to get certification. So above the red line are inputs for the calculator, and below are the outputs, which are the criteria your project would have to meet. So the first set of inputs are very generic project information, what type of units you want to work in, imperial versus metric, whether it's a residential or non-residential project, and that's the only distinction. All non-residential projects are the same. And then whether it's new construction or retrofit. And the retrofit option is kind of a trick question. It doesn't really give you any different standards. You really have to meet the same standards. They do offer some relief for some really egregious existing thermal bridge conditions, like existing slabs meeting uninsulated exterior walls or something, but it's really the same standard. And the next set of inputs are your specific location. So the modeling and even the criteria themselves are based on your specific location. So you can see the map on the lower right. Those are all the locations that you can kind of pick from the drop-down list. So you need to select a location that's close to the project being developed. And that information is used for two things. One, it goes down and helps, it actually is used in the calculation of your space conditioning criteria. And it also is used to identify the climate data set that will then be used in the energy modeling. And also some additional information used in the criteria development are the envelope area, the ICFA, which is the interior conditioned floor area, and for residential projects, the number of dwelling units and the number of bedrooms. If this were a non-residential project, they would just ask for the maximum occupancy. So behind the scenes, the calculator then takes that information you've provided and then spits out these space conditioning criteria. The total heating demand, annual heating demand that is, the annual cooling demand, the peak heating load, and the peak cooling load. And those are in, the units vary. For the demands, it's in kilobtus per square foot per year. And for the loads, it's BTU per square foot per year. And the diagram in the lower right kind of describes what those means if you're not clear what those are. If you imagine your heating season being in red and your cooling season being in blue, the area under that curve is the total demand for the annual demand. And the peak points are the peak loads. So you have one for both heating in the winter and one for cooling in the summer. And just further about the space conditional criteria, you have to meet all four, and there's different advantages for each. So a low annual demand saves on energy and operating costs over the whole year. A low peak load ensures comfort in those extreme condition days. You want to still be comfortable, and resilience, which actually also speaks to the idea that you want the space to still be comfortable even in extreme weather events. And it also helps reduce the mechanical system size. If the peak load is smaller, you can potentially size your mechanical system to be smaller, reducing your capital costs up front. And the last of the criterion calculator results, and it's actually not actually a result because it doesn't change based on whatever your inputs are, is the source energy criteria. And that's the same for all projects. At residential now it's 3840 kilowatt hour per person per year. So that's the kind of per person fair use that we mentioned before. And for non-residential projects, it is based on the square footage of the project, but it uses the occupancy in the calculation of that. So in terms of further explanation of source energy. So it is a source energy requirement. So this will help go through what that actually means. So site energy is the building energy consumed over the course of the year, and that's reflected in your utility bills. So that's actually the energy you're consuming on site, whether it's gas or electric or any source. That's the actual content consumed on site. Source energy is a site energy described above, but includes the losses associated with generating and delivering the fuel. So the site energy times a number called the source energy factor gives you the amount of source energy. As an example, on the right-hand column where we have site energy, and if you're using something like natural gas, that's a fuel, or your project uses electricity, those have different source energy factors that account for transmission and production. For natural gas, the source energy factor is 1.1 because all that's really accounting for is transmission loss and the original fuel going into the system. For electricity, it's 2.8, and that 2.8 accounts for all the natural gas that has to go into producing electricity at a fossil fuel plant, as well as the wind, solar, and hydro that might be directly connected to the grid. So you might look at this and think, well, it looks like electricity is at a real big disadvantage because the rating is based on your source energy requirement, and the source energy for electricity is 2.8 times your site energy. For natural gas, it's 1.1. So it seems like electricity is a little bit of a disadvantage, but actually, as we'll see later, the way the electricity is delivered for heating, it actually ends up being still a more effective heating product, even in terms of the source energy required. The last criteria that isn't a result of the calculation, it's just a standard requirement, is the air tightness criteria. And that's 0.06 CFM at 50 pascals per square foot of building envelope. And this is a very important one. And it's a very stressful one for designers because it's a tested result. So you could design the project, test for it, and if you fail, you fail. It's a pass-fail standard. So you have to meet this, and anybody who's been through this knows that this is kind of one of the biggest points of stress about a project. There's some additional requirements too that get into the weeds a little bit, but Energy Star appliances, and there's also indoor EPA indoor air plus requirements for radon testing, low emitting building materials, and so forth. Now there's a lot that goes under the hood when you enter in your information and it spits out the criteria. And so PHIUS has a methodology that's really designed to be very cost optimized. And it's actually it's baked into where the into the criteria that are developed. So you don't give it any cost information. It's just kind of baked into how the standard is built. And the whole idea is that if you look at this curve on the right, if you continue to pump in measures to reduce your energy costs, you can get your energy cost to go all the way down to zero, which will be this green bar goes down to zero as your energy costs, your monthly energy costs go down. But to do that, you incur capital costs, so mortgage payments. So the idea is that as you improve your property, you'll get some payback right away. There'll be a low point about here. But if you keep pumping money into energy performance to get it all the way down to zero, your capital costs with the mortgage and plus utility bills, your monthly costs, that is, mortgage plus utility bills, may get kind of out of range. So PHIUS criteria is designed to kind of hit this sweet spot. It's not the most cost effective, but it's still cheaper than doing no energy performance measures. So in terms of the process, like we said, you really want to do it during the design and the construction of the project. It pretty much has to be done that way. The standard really has two phases, a pre-certification phase and a final certification. So the pre-certification phase is when the certified passive consultant, optimally, you don't necessarily have to use one, does the energy model and the documentation for PHIUS. They work with the project team and they work with PHIUS. PHIUS goes through three very thorough review cycles. And if the models is all signed off on, you get pre-certified. And then during construction, the passive house verified or the rater will do a final certification, which is the testing and inspection, on-site inspections, and blower door test. In some cases, PHIUS does not require it to be certified, but monitoring in some cases is desirable. There are some grant agencies that require monitoring for grants. The Illinois Clean Energy Community Foundation requires monitoring for a year following just to make sure that it actually meets those targets, but it's not a requirement of PHIUS. So all the modeling is done using a tool called WUFI Plus. It's not a software you tend to fall in love with, but it gets the job done and it's pretty thorough and detailed. On the left is kind of an image of what the kind of interface looks like. Use a WUFI thing, and then there's also this Bible kind of the passive house consultant to go through and really check modeling protocols, because even though you're using software, there's a lot of decisions that need to be made, a lot of approaches that aren't really clear, and the certification guide is really a great source for information on how exactly you need to model certain conditions that might be a little bit uncertain. And with WUFI, you can just import building geometry direct from SketchUp, or you can use the internal wizard for building the model. And it requires detailed authenticated performance information for the R values of assemblies, and in particular things like heat recovery, ventilation, and window performance. It really wants the information in a specific format. In some cases, product information is available off of WUFI's website for some manufacturers, or these AHRI certified product ratings for heat recovery ventilation. You can go to them to get that, but they will look at this information. It's very, very detailed in the review, what needs to go in the model and what PHIUS looks like in the review cycles. PHIUS literally checks every setting in the model, every review, and gives you feedback on them. The WUFI model also requires detailed site-specific information, so local climate data, which you can get from them, and then but you always have to do a site shading study just so that you're representing correctly how the local environment might shade the building, which would impact your heating gains. And it also generates lots of reports. There's lots of detailed information you can collect it looking at it. And this one on the right is actually very valuable because it kind of gives you a breakdown of where all your heat losses are. So this is a winter energy balance report. It tells you where all your heat losses are going. So you can see in this one, there's a lot of loss through the walls. So this helps you look at where you might want to make your efforts if you're not hitting the targets. And then this tells you where the balancing heat is coming from. So the approach it's actually a nice, simple approach. You start with the compact form, try to keep your building as simple as possible. Then go through one, reducing your heating and cooling demands on loads. And that really means looking at thermal insulation, continuous air barrier, managing the solar gains, and heat recovery ventilation. And then number two, reducing your energy use with minimum heating and cooling systems, usually a heat pump, efficient lighting and domestic hot water system. And then finally, offsetting any residual energy use, site energy use with renewables. So thermal insulation, very straightforward. We all know what that means. It reduces the energy loss through the envelope. You want to look for thermal bridge-free design and high performance windows, and limiting the window area to optimally less than about 18% of the wall area for residences. And here you're looking at R values and U values and paying close attention to detail. Thermal bridges create uncomfortable situations where you might feel some radiant cold and also can create condensation risk. So you really need to minimize the thermal bridging. Airtight construction, we saw that was a criteria, but it's really important because what it does is it limits infiltration. Infiltration results in heat losses because air carries with it the heat from the outside, from the inside out, or vice versa. And it can also result in building failure because infiltration is the biggest carrier of moisture through an assembly, which could condense inside the assembly and causing water damage and mold growth. So maintaining the barrier continuity is really a matter of looking closely at the enclosure details. And thermal insulation and air barrier work together. So they work together to allow drying to the interior and the exterior. So really the kind of standard that you see in most passive houses, something like you see here, where you have on the exterior, the cladding, then exterior insulation, your air and water barrier, your structure, which if it's a stud framing may include insulation, the stud cavity, and interior finish. And the beauty of this is any way that moisture goes in, for the most, it's more likely to occur on the outside of the air and water barrier, and also has opportunities to dry both to the interior and to the exterior. And this, you can imagine this being turned to form a roof, turned upside down for the slab. You just wouldn't have an exterior cladding, but it really works on all elements of the envelope. Managing solar gains is really just, the purpose is really just to reduce the summer solar gains, fixed shading at southern exposures, limit windows on the east and west to total of 20% of the total area. And in this case, you're looking at the window solar heat gain coefficient, the SHGC. The next item for energy reduction is balanced ventilation with heat and energy recovery. And this balanced ventilation simply means that the total exhausted CFM is equal to the total supply CFM. You supply air to bedrooms and living spaces and exhaust air from contaminated spaces such as bathrooms, kitchens, and laundry. And here in this case, you're looking for an efficiency. Up to 95% efficiency are possible, and that's really the efficiency of how much heat is recovered from air leaving the building and brought back into the air coming in. So as an example, if you don't have heat recovery, if you look at the upper right-hand side here, all the air coming in for ventilation would would come in at the outside temperature. So in the case where the exterior is at 32 degrees and the interior is at 68, all the air that comes in would come in at 32 degrees. And of course, if there's air coming in, there's air being exhausted, and that would go out at 68 degrees. So it would require 39 BTU per hour per CFM to heat that 32-degree air back up to 68 degrees. So that's why heat recovery ventilation is critically important. If you have 85% efficiency on a heat recovery ventilator, we're ignoring kind of latent heat, which is about humidity, your air would be leaving the building at 68 degrees, but that airstream would be crossing a heat exchanger, which would return that air into the incoming stream and heat it up to about 62.6 degrees. So you see, you're only trying to make up that 5.8 degree difference with your heating system in the building. So that would only require 5.8 BTU per CFM to make up that temperature difference. So there's a lot more into a heat exchanger. The lower left-hand exhibit, has fans, of course, to drive the whole process. There's filters associated with it, condensate drains and motors. So there's a little more complexity to it than this. But if you're just dealing with the amount of heat that you're recovering from the air, it makes a tremendous difference on the overall performance of the building. So it really is one of the key energy reduction, heating demand reduction tools available to you. Then once we get into minimized and efficient mechanical system, we're really talking about heat pumps almost exclusively in passive house. It's not that it's technically specifically required, but you'll find that it really is the only practical choice. And there's really two strategies for heat pumps. You can go with an air-based, which is kind of what's shown in the lower right-hand corner. This is kind of a lower left-hand corner, typical kind of mini split system, or a geothermal based. And geothermals are a little more efficient, but here we're looking at something called the coefficient of performance. The higher the better, and 3.5 is kind of a good kind of range to start looking at for COPs, and they can go even higher. But one thing to know about the coefficient of performance on these is that it's related to the exterior temperature. So this number drops considerably when the temperature gets close to zero. At some point, it'll bottom out, and electrical resistance would have to be used in there, and that's integral with the heat pump. But it can also get up in the 5s and 6 if you're just you're running the heat on a 50-degree day or something, and can get quite high. So that's a temperature. It's not a straight. It's a curve that describes that profile for the CO coefficient of performance with temperature. So why heat pumps? For any energy that you're using on site, basically you take the site energy, which is the heating demand divided by the efficiency. So you look at a source like electric resistance at the top, the amount of site energy is equal to the heating demand divided by the efficiency of your electric resistance. Well, electric resistance is effectively 100% efficient, basically because the waste output is heat, which happens to also be what you're also trying to accomplish. So to convert that to a site energy, you multiply times the site energy factor, which is a number we looked at before. So for electric resistance, you have to multiply your heating demand by 2.8 to figure out your source energy. For a gas furnace, the heating demand divided by the furnace efficiency is then would be multiplied by the site energy factor to get a heating demand times 1.06 for gas. So as you can see, gas would perform much better than electric in terms of source energy. However, you can do much better with the heat pump. For a heat pump, the site energy is equal to the heating demand divided by the coefficient of performance for the heat pump. And for air, that coefficient of performance on an annualized basis tends to work out to more like 2.9. So that works out the heating demand times 0.34 times 2.8, which is source energy factor electricity, gives you a heating demand times 0.095 for the source energy. So in terms of source energy, a heat pump is performing much better than gas or certainly than electric resistance. Electric resistance would be your least desirable heat source. And then for a geothermal heat source, the coefficient performance is even higher. So the source energy can be down to almost half what the heating demand is. Efficient lighting and systems, again, another source, another total energy reduction measure. This directly comes off your energy use. Efficient light, LED lighting, Energy Star appliance, and efficient domestic hot water system. So heat pump based are very effective. You'd be surprised when you look at the chart how much of your energy actually is consumed by domestic hot water. So this is a really big opportunity for energy savings. And the heat pump, using a heat pump based water heater would give you a kind of very similar kind of story that this does, where it's significantly more than electric resistance, significantly less source energy than electric resistance heat would require. And then on-site renewables. On-site renewables are what you use at the end, and it directly, any on-site production just comes directly off of your site energy production. So it reduces your site energy, which means the site energy times the source energy factor is that much less. If you offset 100% of your site energy with photovoltaics, that's called net zero. And then you would qualify for the net source zero certification that PHIUS offers. And the result, hopefully, this is what a report looks like in PHIUS. It gives you some nice green check boxes if you've met all your targets. So the heating demand, cooling demand, heating load, cooling load, source energy, site energy isn't really a target, but if you hit all those, you'll get a nice little checkbox in your PHIUS report. And this is what will be the basis for your certification, in addition to all the other reams of information I'm sending them. Tony, are you on?
Yes, I am.
So this is the part of the question I had. You know, we weren't sure if James with PHIUS was going to join us.
Hey, Tom, I'm here.
Oh, you're here. Do you have slides to show?
I do have a couple slides, yeah.
Okay, very good. I'm turning it over.
Okay.
Well, you have to seize control. I'll stop sharing mine.
Sounds good.
And you can correct any of my mistakes too.
I didn't see too many. I think you're fine. Let's see. Which one do I got to show here? Let's do
this. And I didn't do great introductions, but Tom is an architect in the city here, has done, was the CPHC for a school project. And James, of course, is with PHIUS, and if you are certifying a project, it will probably come across James's desk at some point.
Or my kitchen table now. Either of those, yeah. Hi, everyone. My name is James Ortega. I am a licensed architect in the state of Illinois. I've been with PHIUS since 2015, and I started as part of basically the certification staff. I was actually hired specifically as part of a multifamily research grant that PHIUS got in 2015. So the first couple pieces of my slides I'm going to show tonight are kind of related to how PHIUS has grown, both as an organization and in terms of how many projects we have worked on and certified and all that kind of good stuff. So feel free to put any questions in the chat as we go, or I'll try and save a little bit of time at the end for questions if we got them. And with that, I will go ahead and start. So historically, I think the first passive home technically that was built in the United States was way back when in 2003 by Katrine Klingenberg, who's the director of PHIUS. And she studied in Germany with the Passive House Institute out of Germany. And she thought, hey, this is really awesome. Let's do this here in the United States as well. So that was the first one back in 2003. And we've grown pretty substantially since then in terms of total square footage that PHIUS has had come across our desks. So last year was still the highest year of submitted square footage we've gotten in any year since I've been working at PHIUS and in any year since PHIUS has been around. So despite, lockdowns and shutdowns kind of stuff, passive building design is still going on around the country, which is good to see. And we're hoping to hit at the end of 2021 to be up to around 16 million square feet of submitted projects. Certification wise, projects are still getting built. There were a couple projects that we saw slow down in 2020 where project teams were trying to work around the new requirements for, on-site building and the restrictions and stuff. But we're still looking forward to 2021 and hoping to see a little bit more normalcy in terms of the building sector. And PHIUS is kind of always talking about how we're targeting and shooting for this exponential growth, which is kind of what these graphs are showing here. Another thing I like to highlight too is kind of how PHIUS has grown in terms of, I think Tom mentioned at the beginning, it's called passive house. I personally like to think of it as passive building because we've grown a lot since I've joined, specifically in 2015, in terms of the multifamily projects that we've seen PHIUS come to work on. So these next few graphics are kind of showing the size distribution in terms of the number of stories of projects that PHIUS has worked on. So prior to 2015, so basically 2003 to 2015, PHIUS had about 1 or 2 projects each in the 3, 4, and 5 story range. Jumping forward to the next 3 years, 2015 to 2017, we had a really big uptick, especially in the low-rise multifamily sector. 3 and 4 stories had a lot more buildings coming around those sizes. And since 2017, we've continued to see an increase in low-rise 3 and 4 story buildings. But now we're also seeing some much more decent sized high-rise buildings of the 7, 8, 9, 10, 11, 14, 15 plus stories, which is really interesting for me to see since I've been here since right at 2015, basically. So I've gotten to see basically all of these multifamily projects that have come through PHIUS certification process. And this is kind of, this is the trend I think we want to see in the future. This is what we've kind of targeted in terms of our new certification criteria. So just as kind of a feel for what PHIUS is working on and where things are going, we're expecting to see more of the trend here, seeing more larger buildings come across PHIUS's desk in the next 3-year period from 2021 to 2024. So we'll see how that goes maybe in 3 years. Next thing I'm going to talk about a little bit more. I know Tom showed some couple good slides at the beginning about, oh boy, now I got cats trying to come up on me. He talked about the PHIUS Plus Standard, and I'm going to assume that all of you understood that completely perfectly, no questions, that was super easy to understand. And I'm going to talk a little bit about PHIUS Plus 2021 and some of the high-level updates that PHIUS have made. Basically, we've attacked the PHIUS Standard as kind of a 3-year updating cycle. So in 2015, we launched the first iteration of the PHIUS Plus 2015 standard, which was the first climate-specific passive building standard around. And that basically had dynamic targets that changed based on your climate location. So hotter climates, you didn't need to go as far in terms of the heating to bring that down because that's not a huge source of energy use, but the cooling targets were a little bit more stringent. And then in, of course, cold climates, we're really trying to crack down on the heating. So it basically led to different design strategies for teams depending on where you were located on a climate basis. In 2018, 3 years after the 2015 standard launched, we went through the PHIUS Plus 2018 target creation period, which I think Tom showed a nice little slide in there of the template buildings that we looked at when looking at the 2018 targets. So to keep in mind, for 2015, it was solely looking at climate. So we did cost optimization studies on a single family home in about 110 different climates, and then extrapolated that for the rest of the contiguous United States, as well as Canada and Alaska and Hawaii. For 2018, we kept the climate specificity. So we looked at those that same distribution in terms of climate, but then we also took a look at building size and occupant density. So there was a slide that Tom showed of 5 different building sizes ranging from a relatively small single family of about, I would say probably 1,200 square feet up to a 10-story high rise that we looked at in multiple climate zones at 3 different occupant densities of relatively low, medium, and high density in terms of how many people and units were packed into each of those buildings, because we were pretty sure, and kind of the 2018 standard has proven so far, that the bigger your building is, you've got a lot more internal gains, which is going to affect whether your building is heating or cooling dominated. So that was the second big step PHIUS took in terms of setting our criteria and trying to optimize for different building types as well as different climates. So for PHIUS Plus 2021, the major updates we have so far are we now have a non-residential quality assurance protocol. So up until this point, we're kind of referencing mostly multifamily applicable pieces of our quality assurance protocol. And that protocol is basically related to what the third-party on-site verifier does on site when he's checking, or he or she is checking that the building was built as planned, basically. So that's kind of a new update. We've done some work to encourage net zero design and encourage electrification of all of our projects as well. So I'll touch on that a little bit. And then probably the most different thing that we've introduced now is a prescriptive path for single family homes. And we've had tons of questions and tons of feedback on this, that we originally launched this idea back at the end of 2020. And we've taken our public comments and feedback, and we've tried to address some of those issues. I'm not going to address many of them in this talk, but we are planning to have another PHIUS webinar in the near future that is going to basically tackle all of the finalized versions of PHIUS Plus 2021 and what we're going to be doing with this prescriptive path, because it's kind of a curveball in terms of what we've been doing in the past. So I'll touch on that a little bit as well. This first slide basically is just showing kind of a snapshot of what the non-residential quality assurance, quality control kind of looks like. We've got a version 1.0 out as of November 2020, which is available on PHIUS's website. And the main idea here is that the PHIUS Plus verifier, or the on-site verifier, is basically acting as lead off in terms of making sure that the building is going to comply with PHIUS Standard. But they're also going to use the expertise of the HVAC contractor and the builder to help them get the building across the finish line in terms of what they need to confirm and the documentation they need to get a hold of. This graphic here is basically showing basically the 3 certification paths that PHIUS has for our certification. This kind of flow chart works in terms of, are you a single family, a duplex, or a townhome? If your answer is no, then the paths available to you are the typical pathway that Tom mentioned earlier, the performance path of you model your building in WUFI Passive, you compare the documentation with PHIUS's help to confirm that it's going to eventually meet the targets. And then you do all the on-site quality assurance and get the project either certified to PHIUS Plus 2021, or if you've got enough renewable energy on the project to bring it to net zero, then you would qualify for the PHIUS Plus 2021 Source Zero certification.
And James,
go ahead, Tony.
The driver of the prescriptive approach, is it to I guess, is there a main driver of why prescriptive versus the full PHIUS 2020? Is it the modeling that's seen as the big obstacle, or trying to reach a wider audience? What's the thought?
I think it's a little of both. So the main targets of the prescriptive path, which we see at this point as kind of like, it's the first time anybody's done a prescriptive passive building standard. So we're still looking at this as very much it's going to be a very narrow window of single family homes that are probably going to apply for this path because it's quite restrictive, basically, right? It's code on extra steroids as far as I can tell so far in what we've been developing. So a lot of the pieces of the prescriptive path are going to be very limiting in terms of what buildings are actually going to apply to be able to meet these requirements. But the main ideas are to take the first step into trying to reduce cost. And we saw a big piece of the cost was the time and energy into trying to have to model, especially for single family homes where, the cost benefit and how much money you have to spend to model and go through the whole certification process of doing a single family home modeling in WUFI passive is not necessarily gonna, net out and kind of save you money in the long run. If you're doing a multifamily building, certainly the costs and stuff are a lot higher, and it's not a significant more amount of work in terms of modeling to be able to get a multifamily across the finish line. But we're basically trying to take our expertise because since 2015, we think we've got single family homes pretty well honed in on, prescriptively what are we expecting to see when a project comes through the certification, like across my desk, basically. I have a pretty good feel even before I start to open the WUFI passive model, if what they're proposing in their plans is going to look like it's going to pass muster, basically. So our main goal of the prescriptive path is to reduce cost and time spent up front when we feel like design teams at this point should already have a pretty good feel on what they need to do to design the project to get across the finish line, and more basically give them the prescriptive path as an option to, hey, if you don't want to keep up on the newest energy modeling softwares, you don't want to spend the time to try and go through all of these nitpicky criteria that PHIUS has created, use this more stringent but basically easier path in terms of the prescriptive path that's maybe could cost you a little bit less money in terms of having to spend all that time energy modeling and stuff, when we already feel like we can give some very good outlined information to make sure that the project is going to perform with prescriptive options. Gotcha. So yeah, I think those are the main two. I think Katrine has some other grander ideas, right, about just expanding in general. And we would love to see, a spec home builder come up and go, okay, we've been doing zero energy ready homes for a while, or some kind of, Energy Star homes or something like that. And if we can point them to, a prescriptive path that's easy for them to read what they need to do and just take that information and run with it, we would love to start seeing, passive developments all around, right, of single family homes. So this is kind of the first step in that direction. So basically going all the way back up to the top, right, if it's a single family home, a duplex, or a townhome, and it's a yes to that question, then you can start to wonder, okay, are you going to want to do any WUFI passive modeling? If the goal is not to do energy modeling, then the prescriptive path is maybe a path you want to check out and see if the project is a good fit for it. And I'll talk through some of what these prescriptive requirements are, not in great detail, but at least high level stuff. And basically, if the prescriptive tables aren't met, then you kind of have to circle back. If you still want to be certified, you always are welcome to go from the prescriptive path into the performance path. That's always an option for you if you want to. So this is kind of the rough flow chart of kind of what we're thinking in terms of which very specific projects would go for the prescriptive path versus the typical path, which is all the two green ones on the left are basically PHIUS's business as normal for the past several years. Okay, let's go. Next slide. So I'll talk a little bit about the first option here. So PHIUS Plus 2021 is what I'll talk about next. So this is the performance option if your project's basically not going to be a net zero building, is what this next slide is referring to. And there's a lot of text on this slide. I didn't realize how much there was until I actually saw this again for the second time today. But basically the takeaways here are that we have updated our source energy target a little bit. So Tom had mentioned that PHIUS has this target based on a fair share of carbon per person, and we still firmly believe in that. But we've seen several projects over the past few years, especially since 2018 came around, where that fair share of carbon is a little bit tough to determine, especially in a multifamily building where how do you determine how many people live in a multifamily project that's all studio apartments? Are we really expecting only one person to live in every single one of those units? Or, with today's economy and the way that people are kind of moving and stuff, PHIUS's typical estimate of the number of bedrooms plus one is how many occupants are living in that house or a unit, is not necessarily the best metric in terms of trying to determine how to limit source energy. So we've now included a source energy target that's also based on unit density, not just occupant density, which is a little bit of a strange distinction to think about until you see a graphic of it, but I hope the next page will show you that. Non-residential target stays the same. It's a per square foot metric. The only differences now are that as part of our efforts to encourage electrification, we're using a new source energy factor that's based on future electric grids in an effort to say that basically in the future, we're going to have more renewable energy in our grid, and we're basically going to bring that source energy factor. Previously, it was the 2.8 versus 1.1. We're basically narrowing that gap. And we're looking now at a source energy factor of 1.73 for electricity versus 1.1 for gas. So that's probably one of the bigger changes that we're trying to implement: more electrification, make projects more incentivized to do basically what Tom was saying most projects already do, which is to use a heat pump, because it makes a lot more sense from a source energy point of view because they're more efficient. Again, previously it was this 38.1 for non-residential, and it's dropping down to 23.5. That drop in ratio is the same as 2.8 down to 1.73, as is the 38.1 to 23.5. So it's not really getting more stringent. It's just basically changing at the same rate as our source energy factor changes. The last piece on here, the stuff below the orangish yellow line I've got going on here, is that for PHIUS Plus 2021, which is if you're not going to source zero, but you're doing performance modeling, we are going to have electrification readiness is going to be required. So basically, if you've got a gas hot water heater in your proposed project, it's fine. You can keep the gas hot water heater, but you will need to provide a plug for a future electric water heater to take over that space. Or if you've got heating equipment, if you've got a natural gas furnace, you're going to need to provide an electrical outlet that can support a future electrical heating or cooling system. So those kind of things are also trying to get electrification as part of the path forward for all of our new construction projects. And we've got a little bit more specific language on this. We've put out a standard setting document that's in draft form right now on PHIUS's website. So if you have more questions on that, feel free to look there. And this graphic here is showing you, kind of circling back to the residential updated source energy target. So again, I mentioned that was previously based on a fair share per person, and now we've adjusted it basically so that it's on a fair share per person, accounting for occupant density and unit density. So in the previous version, again, there's kind of a lot going on here. So we'll start top left. This is looking at kind of a typical low-rise project that PHIUS might see: 3 stories, 38,000 square feet, 58 units. It translates to about 650 square feet per unit, basically, including corridor space and amenity spaces. And so the big gray line kind of going across the whole bar of this project through the middle of this graphic is showing that was the old PHIUS target for certification. So for our PHIUS Plus core target, which was looking at on-site conservation first, was looking at basically 5,500 kilowatt hours per person per year. that target is basically you're allowed to use on-site photovoltaics to help offset your source energy use. When you start to look at a building of about this size, you reach a limit pretty quickly on how much PV you can actually fit on the roof. And the problem was that basically, depending on how densely the building was populated in terms of not only occupants, but how many units were in the building and the size of those units, meant that basically that 5,500 became very, very difficult to meet as soon as you got to a studio apartment building. So in the first column, so again, I'm modeling the same building, same envelope, windows, and mechanicals. The only difference between each of these black vertical lines is what is the unit distribution in this building. So in the first column, if this building was all 2-bedroom apartments, we're assuming like 3 people per unit. That's a lot of people in this, pretty small building. Because our old target was based on the per person metric, it would have met, that red line shows that it would have met, it was underneath that 5,500 by quite a large margin, and it was meeting it no problem. Looking at the second column, the red mark is pretty close. If you just switch this building to 1-bedroom apartment building, 1-bedroom units, which at 650 square feet a unit, that's still a pretty normal sized 1-bedroom apartment. It's just barely under that 5,500 metric. And then if you move out even one further and you're doing some kind of a supportive housing or affordable housing project where they don't really need 1 bedrooms, they need a bunch of studios in this particular area. The studio one just never going to meet that target. It's almost double the old target. So the PHIUS Plus 2021 target, which is the new horizontal black line on each of these columns, is basically now scaling the requirement for source energy with the unit and occupant density, not just having a static number. So you'll see that even though each of these types previously, it does result in a little bit different kilowatt hours per person per year, you got to remember that this building is expected to use about the same energy use on an annual basis. So this new target is basically scaling and it's staying about the same margin underneath. And each of these projects would now qualify for PHIUS certification, whereas before the studio building basically would have been shot right out of the water because there's no way you could have met that previous target. So that's one thing PHIUS is trying to expand, specifically because we've seen quite a few of these really dense buildings, these studio type buildings, where the on-site conservation first target was basically really, really hard to meet, and kind of unfairly so. So that is where that one is at. This next slide is now talking about, again, the performance path, but if you want to go all the way to net zero with your building. And for this particular path, unlike the previous discussion, we don't actually require, or we don't allow fossil fuel combustion appliances on site. So for the source zero tier, no gas appliances are allowed on site, no fossil fuel. You can still use biofuel. So basically wood burning stoves are still allowed in this situation, but anything that's burning oil or natural gas is not gonna fly for PHIUS source zero certification standard. And then the other part of our source zero path basically is that we allow not only on-site renewables, but off-site renewables to help offset your energy use as well. So this table basically outlines that we're aligning for the most part with ASHRAE 189.1, Appendix J, and Architecture 2030 in terms of their definition of a net zero building. Now I'm gonna talk a little bit about the prescriptive path. So I alluded to this earlier. We've got another path for single family homes where you don't necessarily want to do energy modeling. And this graphic basically outlines all of the things that we had to think about when making a prescriptive path that we had to have rules for, basically. So we had to have some general scope limitations. We had to limit solar protection, mechanical ventilation, air tightness, heat transmission, moisture risk. We were working on how we implement compactness as part of it. And then we also have some active system requirements in terms of your mechanical systems, your lighting, appliances, and how you're providing hot water. So I will kind of skip through these a little quickly, but so on PHIUS's website, this is basically what our website looks like right now. It's called PHIUS Plus 2021, and all of this information is available for public review. You don't have to, sign up for anything. Take a look. We've got a public comment form. We've got a webinar recording that we talk more in depth about what we were thinking for 2021. We've got a standard setting documentation. And then we've got at the bottom of this page, there shows up, it says a design review checklist, there's a calculator, and then there's an assistant. The checklist is basically the meat and bones of what we're proposing for the criteria of the prescriptive path. And the calculator and the assistant are basically playing assist to the review checklist in an effort to kind of make it clearer based on your different locations of where your project could be. So this is kind of where everything is located. If after this recording you want to see a little bit more in detail what PHIUS is proposing. So PHIUS's prescriptive path, this is the general scope. So it really only applies to single family, detached or attached residences. We've got an ICFA per bedrooms has to be at a limit basically of a little bit of less than 900 square feet per bedroom for your house. We don't allow fossil fuel combustion. So again, super limiting. So we still see a vast majority of our projects are going to be in the performance path. We're not going to allow jetted tubs or indoor pools in the prescriptive path. And that is mainly because we're not going to have the same kind of eye on humidity control in these prescriptive path buildings. So that was the main driver for that piece. And as in all PHIUS projects, there's no natural draft fireplaces allowed in the prescriptive path either. Some of the passive measures and co-requisites are all kind of the same as our typical PHIUS requirements in terms of the co-requisites. All of these projects are still going to be Energy Star, DOE Zero Ready homes, and they're going to have to comply with Indoor Air Plus, EPA's Indoor Air Plus. Some of the passive measures that we're introducing at a high level are air tightness and we're going to actually require a preliminary blower door so that we know that these prescriptive homes are on the right path to meeting the air tightness requirement. Solar protection is going to be limited on a total window to wall ratio basis. There are going to be some overhangs depending on your climate that you'll need to introduce, and there will be solar heat gain coefficient limits based on the climate as well. We've got moisture risk and condensation limits, which kind of reference some of our performance-based requirements, but we've got more options for them in the prescriptive path. And then we're basically have some rules in an effort to eliminate thermal bridging. Some of the other specific requirements of the prescriptive path, the climate dependent ones are listed on the left. We've got some building dependent things on the right. I'm not going to go through all of these in that much detail, but basically we tried to look at every piece of a passive building and do our best to have rules basically on all of the things we would normally check during our typical performance review and turn our performance modeling into this is what PHIUS is going to actually require in terms of piece by piece assembly of your passive house here. This one here is something we created pretty recently. The prescriptive path is actually a little bit of a weird piece to look at. These R value ranges here are truly for reference only. So they're kind of listing the minimums and maximums of each climate zone range in here in terms of what you can expect for roofs above grade, below grade, and then all doors and windows are listed in the U value table down at the bottom in terms of like the ranges that you could expect to see. And I'm saying it's a reference only because our criteria calculator that comes along with the prescriptive path literally looks at the city you're in to tell you your city specific R values. It's not just a general climate zone type rules. But this is for reference so people can kind of get a feel for, where could we expect to fall if we're kind of in the middle of, say, climate zone 5A or 5B, for example, like Chicago is. So you'd be looking at a roof between R60 and R80, above grade walls between 32 and 52, below grade stuff between R16 and R32. R32 is probably on the colder side of climate zone 5A or B. And then from a U value in terms of windows, you're looking between 0.26 and a 0.13 U value range. So again, for reference only in this case, but
so this is also probably tied to zip code. You plug in the zip code and it spits out a specific number for each of these, and that's independent of the shape of the building, or a few other factors, as long as it fits within those kind of maximums. So let's say I plug in Chicago and I get an R60 house, R60 roof. Do you have a sense for sort of my sense? Or I think I heard you say that these are more conservative. Do you have a sense for how conservative they are? Like, are you going to end up adding 5–10% more insulation than if you were to model it?
Yeah, I would say probably. So we basically, to make sure that we were falling in the ranges, we went through and we did basically took all of our optimization data that we did for the performance standard, and instead of finding correlations for the space conditioning targets of heating and cooling, we found correlations for R value of walls, windows, roofs, and floors. And basically we took those curve fits, and instead of doing a best fit line, which would have gone right through the middle of all that data, we did a inclusive curve fit. So if if Chicago picked R60, for example, as part of the best fit solution, but another city was, quite a bit higher than that in the same climate zone, it would basically choose the higher city. So I would expect probably, like for roofs, for example, I think we added about an R5 or so versus what we would expect in the performance path. And it varied depending on the range that we looked at for like walls and below grade. I don't think it was as significant because the roofs have the highest variable between climate zone 0 of like R48 up to climate zone 8 of like 164. That's a pretty big spread. So yeah, I would expect it probably 5 to 7%, I would guess, for like roofs, for example. Walls might not be as significant there.
Gotcha. Okay.
And then the U values so all of the R values, roofs, above grade walls, below grade walls, were based off of our climate specific optimization studies, and then doing best curve fits, and then taking on top of that basically inclusive curve fits. For the U value ranges for the doors and the windows, or in this case, it's just fenestration. So this includes skylights as well. We set these requirements based on PHIUS's comfort criteria. So we've got a comfort criteria calculator for depending on window height, and we basically locked in a static window height and then assigned that kind of per climate zone. So that's where these ranges come for the windows. Let's see. And that is it for me. I'm going to kind of leave you with this table and see if we had any questions, I guess, during this.
Thank you, James and Tom. Excellent information. I did just share the results from our poll. I know oftentimes when you're in this kind of presentation, it's always nice to kind of survey who's in the audience and what kind of why you're here and what you're looking for. So it seems we've got somewhat of a mix here. So glad to see all the boxes checked. If you guys do have any questions, you can type them into the chat, or if you want to take yourself off mute, let me know. Certainly happy to take a few questions here. I do want to, I guess, also plug our newsletter. So if you're not currently getting our Passive House Chicago newsletter, You can easily request that via our website, and it's also listed on our meetup site. So couple ways to get that. And then we do this once a month. So February will be sort of expanding on this Passive House 101 theme. And then in March, Tom Basadilli will be focusing on renovation aspects. So really an interesting different take on some of the challenges that are required of a renovation versus kind of a new build. James, I had a question for you about, I know there was a slide about certifications this year, and it's always interesting to see kind of where the trends are hitting. I know in past years, multifamily was still taking off in terms of units and square footage. Are you seeing any impacts or changes since we're living in the pandemic and there's all sorts of new normals that we're adapting to? Are you seeing any sort of change in that trend because of that?
If anything, we're seeing more multifamily, I think. Probably like March last year, probably March through May, I think I had like 2 single family homes, like custom single family homes come across my desk, but we still had like 20 plus multifamilies coming from the affordable sector. And I'm not sure if that has to do with the affordable projects already were guaranteed their funding, at the beginning of the year, so they could continue to move forward. But we've still definitely seen the trend of more multifamily projects still coming. And yeah, this year, again, we had the most submitted square footage of any year since I've been working here. And it was in large part due to the multifamily projects are still coming pretty strongly. Now that we're in 2021, I think on like January 5th, I had like 11 single families come to me, like basically right at the beginning of the year. And I was like, okay, this is a little weird, but I mean, like they come in buckets like that sometimes. But yeah, for sure, it's been the multifamily is still the trend of that's coming across more, especially in the Northeast. They got tons of incentive programs for the affordable multifamily housing over there in New York and Connecticut, Massachusetts, and Pennsylvania.
Good. I see we just got a question from Pam Hutter about geothermal and its application in passive house projects, and whether, or I guess maybe the first question would be, how common is geothermal for passive house? Is it compatible? And
yeah, no, that's a good question. I can take this one to start with. So I don't see that many geothermal projects, and I don't think it's because they're not efficient. It's because they're expensive. Usually you have to dig a lot. You have to get, surveys done to make sure that how much heat your soil actually holds and is going to be able to transfer to your system. But by and large, they're just very expensive, I think, is probably the biggest starting point hurdle. They're much more common, I think, in the Northwest. I see a few single family homes that go for geothermal up in the Northwest, but I also don't know the financial situation of those custom homes up there. Those people are probably pretty well off. For a typical person living in Chicago, I think geothermal is probably not in the cards in terms of cost and permitting and making sure you even have space to drill for a geothermal system. From the perspective of just straight up efficiency, oh, those things are awesome. Like they're super, super efficient. It comes with a cost. And as far as PHIUS's cost optimizations went, I don't think the optimizer picked geothermal that often. For sure not for single family. Like it just doesn't pan out in terms of cost. Maybe for a multifamily, if you've got like a big side yard space to do that kind of a thing. But yeah, efficiency wise, super amazing. If it's worth the cost, it's kind of up to the project team. I don't see a ton of them.
And I think the case studies that I've seen that do have geothermal, I've seen them a few times on larger multifamily commercial projects where just the loads are much more substantial and I guess maybe warrant the first cost of the bore rig to come out and drill some bores, and or just have, you know, significant loads that would still need to be addressed. And I guess too, I think so. I'm kind of curious how often you see the quote unquote brine loop or the what would it be, it comes from other names, but
Like
basically
a subsoil heat exchanger for the
Yeah.
UV.
Yep.
So I don't see them that often either. The most common one we'll usually see is the ComfoFond, which is a Zender product because it comes as kind of a package system that you can install with your Zender ERV. That's probably the most common one I've seen.
And so that in some ways is, I'm going to say, a poor man's geothermal system in terms of it's often just laid, is more of a horizontal, so it's not a deep well. Oftentimes part of the excavation of either the basement or the side yard, coils can be laid in the foundation, and then that, if I'm right, just serves as a preconditioner for incoming air to your ERV versus connected into your heat pump.
There's no heat pump associated with it, correct?
Right. Yeah, usually what they use, that kind of a brine loop or a subsoil heat exchanger, is typically for defrost protection, basically, like passively defrosting your ERV core and using whatever kind of extra heat you get from it to help precondition that air. So basically it's helping to passively increase the efficiency of your ERV by, instead of bringing in 32-degree temperature air in the middle of winter, you're bringing in like 40-degree temperature air or something like that. So you're basically just, it's just acting as a passive way to provide a little bit of extra heat to your air before it even gets into your house.
Good. All right. Well, I don't know if there are any other questions, maybe one more if there are, or if not, we can sign off for the evening. I want to thank again Tom and James for their time and their presentations. And I hope to see you all again next month.